All right. So we stopped somewhere around here. I just stopped to think on this slide. But yeah, before we get into it, reminder today: if you're changing projects, as expecting to receive your project proposals today. Um, yeah. Other than that, yeah. Any other questions before we start the class? Anything else people want to talk about? Oh, we only have 10 people today. All right. So it looks like nobody's got anything to ask. So let's get into the slides. So I think we stopped here. We were talking about on-chip multiprocessing last time. And so, when you kind of have multiple processors on the same chip, it allows you to be a little more efficient because a lot of the extra logic that you have to build in can be shared among the different processors, as opposed to when you have symmetric multiprocessing, where you have two separate CPUs, and then you need to build things that allow them to access any memory, or synchronize between their caches and things like that. So when you look at designing a chip, like a single chip with multiple processors, there are many possible ways to connect each core to the shared set of resources, which Intel likes to call the uncore. So the L3 cache, access to I/O, access to the memory controller, and things like that. These tend to be shared among all cores, and so how do you connect these cores up to the uncore? So we're going to look at a bunch of different topologies very briefly, right? That we're not going to go into too much detail about all of these things, just so that you're aware. So possible topologies. The simplest one is a bus. A bus is just a single shared substrate that everybody connects to, and then at some point, if one core decides to use the bus, no other core can at that moment, right? So this is kind of the most basic way you build an interconnect. Now, another possible interconnect is a crossbar. And the bus was, very common. You'll see this in a lot of processors. Like, not particularly sure which specific one this is, but this is some 4-core Intel CPU. We'll see a crossbar. Crossbar tends to have a grid-like pattern with switches at every interconnection. So the bank, one cache bank, is connected to every core by a number of switches, and then every core is connected to every bank and the memory controller, along its path. So it's kind of a grid. So the crossbar allows an any-to-any interconnection, and each switch, has 4 links and so on. So a crossbar is, an example of a chip that had a crossbar is this UltraSmart T5 from Oracle. It's got these 16 cores. There's a bunch of L3s over here. There's a crossbar here that allows you to connect from any of these cores to any of these L3s. And I'm sure the same crossbar is also connected to all the other stuff here, right? The SerDes, the PCIe, and this coherence controller, things like that. Now, improving on the crossbar, there's one issue with the crossbar, which is if you're it takes a lot of space to implement all of these switches, right? And there's 4 ports in each switch. So a different way of you'd implement this is just with a ring, a closed loop, where each core is connected to the thing by a switch. So the switch has 3 ports, and you can go in either direction in the ring. So you can come out of the core and then go left or right, right? You can go to the memory controller, you can access coherence traffic between the cores. You can send traffic to access requests to any of the banks and so on. This is a lot simpler and cheaper to implement because the switches have less ports, there's less switches overall, and there's less wiring. And you can move in either direction to reduce latency. Example of this was the Sandy Bridge. You had 6 cores, a shared L3 cache in the middle, and then you had the ring and all that implemented. Kind of inside here somewhere, right? So this would be one port, this would be one stop. The L3 is banked up, the banks will be one stop each, and the memory controller is some number of stops. I mean, some number of entries or switches there. Another one that we can look at is a mesh. Now, mesh is kind of like crossbar, but the difference here is that every element is connected to one switch, and then the way you communicate with everything else is you move up and down. So every switch has 4 directions and a 5th port that goes to the resource it controls, right? So everything is kind of like in a grid, in a tile. You have these tiles and you expand by tiles. This was the, there's actually a company that built a 64 core, very early 64 core processor out of this style of interconnect because it scales really well, even though it's a little expensive to build these switches. But you can replicate the pattern very smoothly, and then data transfer takes place simply as a packet switching network. A simple issue that rises with this kind of organization is that placement of computation becomes very important, because if you have to communicate with something that's here and there, it takes very long to transfer to do coherence traffic between these cores or whatever. So you actually need to find ways to place computation threads as close to other computation threads that they're dependent on, or find a way to propagate data, in waves or something like that. So it actually requires, for it to be used performantly, you kind of have to change the way you think about programs. So it wasn't that much of a success, but it's still an important way of looking at interconnects. And then if you take a tiled or a mesh and you connect the edges so that you don't have to traverse the whole link, you have an extra dedicated link, you get a torus. And a torus is just you take a mesh and you connect the last things. And this just avoids having to traverse the whole way through something. There may be faster paths. Just you're trading more wires and energy for latency. So yeah, just a brief look at the different types of interconnects that you can have on a core. We're not going into much details. There's a whole topic of specialization for many people, but yeah. Questions on any of this? Nobody has any questions? Okay, moving on. Um, so we've looked at, SMP, we've looked at symmetric multiprocessors where you have multiple cores that, you have multiple chips that sit on the same motherboard. And then we've looked at chip multiprocessors, and then how do you interconnect them? So why have we gone in this direction of chip multiprocessors over SMP? It's kind of a false question, but let's deal with it for now. Um, CMP tends to have less. It tends to have more um, resources shared between cores, so you end up with less power for the whole thing, right? Like, because most interface logic is on the chip, so getting signals to it is cheaper. You have to multiplex it between things, so you can have simpler multiplexing um, structures when the distance that you're traveling is less. Allows you to probably run things faster and so on. It also uses less power than multi-chip SMP because you're running less distance, right? Your signal's traversing less distance, and it becomes cheaper and it's more efficient because you're you can use you can implement multi-core processors instead of having a very aggressive out-of-order machine that may not be used fully. Here you can take advantage of multi like task level parallelism instead of instruction level parallelism, and maybe because you're sharing things on the same chip, you get better use of hardware. So now we've got multiple cores on a single chip, and we have multiple we have multiple execution units. So we need some way of programming such that you're able to take advantage of these multiple execution units. So this is typically multi-threading, right? Like if you had and we're not talking about multi-threading just from a software perspective. There's also hardware multiple threads. So you can look at if you had a single uniprocessor and it was 4 to 6 wide, you'd be really lucky if you got a 1 to 2 IPC and instructions per cycle. So you end up with very bad utilization of the hardware that you have, right? The transistors that you have. So with symmetric multiprocessing, if you had like 2 to 4 CPUs, you would be able to run things. You'd be able to keep the hardware busy if you had independent threads. But if any of your threads had dependencies, then you have poor utilization as well. But then you can do something like coarse-grained or fine-grained or simultaneous multi-threading, where a single large uniprocessor is treated as a multiprocessor, right? Like, so if you have one core, now this one core doesn't run one thread of execution at a time, it can actually run multiple. There's different ways of doing that, and that's why you have 3 things there. So the only additional hardware support that you would need for running multiple threads of execution is you need a per thread PC, program counter, and then you'd need a per thread map table or architecture register file or whatever. The stuff that's holding all the data for each thread, right? So each of these cores and threads will appear as multiple CPUs, and OS designers still call them CPUs. So we'll look at each of these things in terms of how they're used. So if you had a scalar pipeline, you had one thing executing on it, and you have something like this, where the white represents nothing useful being done, and then the the red is some task working, right? And this is a very high level, like abstract view of the thing. So if you went from this to a superscalar pipeline, you'd still be able to maybe issue a couple of different um, independent instruction streams within the same thread of execution. So you get like some amount of parallelism that you could take advantage of, but then you still have a lot of these white zones where there's probably data dependencies or um, other lack of lack of work that you could do at that point. So there's a lot of utilization that isn't useful. Even with like out of order execution and sophisticated branch prediction, sometimes this is just not going to be enough, right? So there's actually a bunch of studies that have shown that for the 21264, which is an alpha processor that DEC used to produce, or Compaq, whatever, used to produce back in, I don't know, the early 2000s, I think. The functional unit utilization, so the ALU, the floating point unit, whatever, was somewhere under 50%, right? Like as you could keep the machine doing useful work like 50% of the time. And this tends to get worse. Now there's a trade-off there, which is that even if this gets worse, that is in some sense you have so much performance capability that the software is not using it, and so your single thread performance is great, right? You could write better software, but the hardware is already optimal. So now, starting from the fact that optimality exists, we can actually do better without hurting single thread performance, well, most of the time. So that's kind of where we go into the chip multiprocessing aspect of things, where it's like, you take the resources that you would have dedicated to, say, a four-way superscalar core, whether it's out of order or not, and then you kind of split it into two cores, right? So now you have two independent threads of execution or tasks running, and you might be able to use the hardware a little better. There's a slight amount of performance loss for each individual thread, each individual task, because in the earlier case you had four pipelines executing just that one task. So you have these four, even if we were to just use this thing that's shown, which is some bogus example, but you still had these four pieces of work that were done in that time frame for task A, whereas here those four pieces of task are being dedicated to doing work for task B, right? So there's some amount of loss, but it's the added benefit of being able to do another thing just means that it works out better in most cases. You might have changed your programming a little bit. But if you had only one thread, only one task that you were trying to run, then the chip multiprocessor is kind of useless. So then you get into like, can we do better than this? So then we can do multi-threading, right? Like when you have a given when a given task takes a long latency operation, like an L2 cache miss is something, you can say, okay, you know what, I'll context switch over to a different task and I'll use that instead. So this is hardware level context switching, right? Like not OS context switching. So you could say, do dedicate the whole processor to some task A, And then when A hits an L2 cache miss, for example, it's going to take for a long time. You can switch over to running task B, right? The issue with coarse-grained multi-threading is it only absorbs these long latency operations. So you'll still see things like this, right? Where there's nothing useful happening. So in those cases, you tend to have, not very good. It's still, we can do better. There's opportunity here that says we can do better. Yes, somebody had a question.
How does the hardware know which task to switch to? Because it has to be a thread of a process, correct? It can't be a different process. Well, it could be a different process, but essentially you need to share the same memory space, or no?
So that depends. If you're so switching memory space has a certain cost to it, right? Like it takes a certain amount of time to flush whatever state that you have to, change the CR3 register, flush the MMU, the page table, the TLB, or whatever, all of that. So if your operation is actually that long, then you can switch it. But typically, you're right. They don't. You typically don't switch to a different process with a different address space entirely. But you could.
Hyperthreading, or is this different?
Sorry.
Is this the same as hyperthreading, or is this different?
Well, hyperthreading is different. We'll see that as symmetric multi-threading.
Okay.
So this is coarse-grained multi-threading. This is you have multiple threads in your single process, and you switch between them. So one could be, I don't know, Chrome, for example, has multiple tabs open. Each one has its own thread. You could be running different things. So you could have maybe one tab is one process, and one thread fetches video data, one thread decodes it, and one thread displays it or whatever. And so you just keep switching between them, right? Something like that.
How does the hardware know like where to even access this thread? Like, how does the software make this information accessible to the hardware?
So when you launch a thread, you've started a set of execution, and it will have a different what do you call it? It'll have a different starting point. It'll have a different. So most of the time, these.
Well, I think my question maybe is a little bit more coming from Joss. So maybe we can talk about this offline then.
Okay. Yeah. So another way to think of it is threads to a programmer are a different way of thinking than threads to hardware, right? Like, so the processor does not treat processes and threads differently. So any new context of execution, whether it is a new process or just another thread in a process, is treated as a thread. And so when you launch a new program, you start a new set of things associated with it. That's a new thread. Whether you're in the same address space or not is for software to take care of. So it's up to the OS to make sure that you're not executing things that are in different address spaces at the same time, if that makes sense. So yeah, coarse-grained multi-threading is when you switch between threads. So the granularity of mixing is really coarse. That's why we call it coarse-grained. So it has a little bit of a loss in single thread performance, because while one of your pipelines takes a long latency operation, you might switch, so you lose some time for the switching, and the other pipelines are losing some state, right? Like they're not losing state, but they could have maybe finished executing in that time. So you might lose a little single thread performance. And the downside is it tolerates only long latencies. So one thing that happens here is you can sometimes cores will implement a thread scheduling policy. You'll designate a preferred thread, and then you'll switch to thread B on when L2 miss happens, and then back to thread A when the miss returns, right? So yeah, it's the long latency actually is pretty long, so it's like you cannot tolerate. You can't use this for any latency shorter than typically twice the pipeline depth, which is really long. And this doesn't give you as good performance. So what is a pipeline? How would this be implemented? How does the pipeline look? So you tend to have multiple. You have a thread scheduler here that decides which of these colors you're going to use, and then every structure that kind of keeps track of data or execution context stuff is double the size and maintains or split in half, and each thread only gets half, whatever. And then you have multiple register files and everything is multiplexed. So this is kind of how you'd implement coarse-grained multi-threading. So then, because coarse-grained multi-threading doesn't perform really well for something that is a short miss, you could think of making the granularity of multi-threading finer. So I think the most obvious way you could do this is to kind of do a round robin fine-grained multi-threading, right? Like so, maybe some unit of time you execute thread A, some unit B, C, and so on. This is great when you have a saturated workload, so you have a lot of threads and you keep doing that, that's fine. But when you have some fewer number of threads and your processor is hard-coded to execute, say, four a multi-threaded with fine-grained multi-threading, then you kind of end up with all these wasted slots, right? And that may be just because at this point this thread was waiting for some operation to return or whatever. It's not that the thread doesn't exist. It's just it may be waiting on memory or something of that sort. And if you have any intra-thread dependencies, you have performance limits, right? So the fine-grained multi-threading is like the extreme where you sacrifice a lot of single-thread performance because you're constantly doing these switches, a lot of overhead from that. But it tolerates everything, right? Like any misprediction, any rollback, whatever, it gets tolerated. And it's a very simple thread switching or scheduling policy. So you just switch threads between, you just cycle between them, right? It's a round robin. And then the way you partition your pipeline, it's just dynamic. There's no flushing needed. It's just, you have more state that you maintain for each thread. So the length of the pipeline also doesn't matter. So similar to the coarse-grained scheduling, the way you'd do this is you'd have a thread scheduler, each data structure that keeps track of a hardware structure that keeps track of which thread's executing, has multiple entries, multiple colors, whatever, and you kind of this is kind of how you'd implement it, just at a very abstract, high-level view. Can we do better? Does anyone want to take a guess as to how we can do better than this? What is one, I don't know, policy in this style of execution that leads to this, right? And how could you do better, or what could you relax to get a better performance? No ideas? How about this, right? So the issue with why you end up with so many lots of stalls, right, is that you're trying to execute a thread. You're trying to switch into a thread that may not be ready. So because you're using a very simple round robin scheduling policy, you could say, hey, switch to thread 2, is there work? No. Okay, switch to thread 3, is there work to do? No. Switch to thread 4. What if instead you actually just went from thread 1 to thread 4 because you knew that 2 and 3 are stalled? There's nothing useful that they can do. And so the way that works is, or what that's called is simultaneous multi-threading, which is you actually, have a single shared you kind of execute all threads at once, right? You're not switching between threads, and whatever's ready, whichever instructions are ready, you issue those. So that can sound like it's a little confusing, but we'll see an example of that in a second. So the way, so like you could, in one time slice, you can see that the 4 ways of the thing are executing random colors, and then there's no like real pattern to what goes next, right? It's just whatever's ready, whatever's the oldest instruction. So this typically gives you the the best utilization. So it tolerates, again, because it's the similar to fine-grained multi-threading, it tolerates all latencies. Its thread scheduling policies kind of like round robin, but it's not. It's round robin with a readiness check in some sense. And this tends to be implemented as hyper-threading, as Sarah was asking, from the Pentium 4 era onwards, and the Alpha 21464, which was cancelled, was supposed to have this, I guess. So the way you'd implement this, right? Like it looks like kind of like this, where if this was the original out of order pipeline, you would now have the same issue and predictors and stuff in the front end, kind of have round robining between the threads, between the 2 threads, so that you are fetching and dispatching different instruction streams. And then when you're in the backend, or the out of order execution engine, whichever instruction is ready at any given time, you execute that instruction. And then you maintain the in-order guarantee by having the ROB that keeps track of instruction order. And so this way kind of uses the fact that your out of order execution can go, it doesn't need to like hold on to patterns. So you can find the next instruction that's ready to execute, has all its data available, and execute it, and then restore things. So this is simultaneous multi-threading, otherwise called hyper-threading by Intel. Right? So yeah, questions?
And this hyper-threading can be done across processes as well, not necessarily threads of the same process, right?
Not really, no. Because the instruction cache and the data cache are shared. So if you were able to have, you can implement it across different processes or different address spaces. If your caches were tagged, if you're able to tag your cache with, oh, this piece of data belongs to this address space, so you have some kind of address space ID or something like that. And if you're able to tag those, then yeah, you can run unrelated processes that are in different address spaces, as long as you're taking care that they don't touch instructions or data that aren't correct. But
is that something that's done, or
not as tagged caches exist, but for a very different reason. I don't think there are processes today that actually do SMT across multiple address spaces. Tagged caches exist. Actually, I could be wrong on that. I don't know. But I know that tagged caches exist as a way to, because caches is so big when you are doing like virtual machines or even just regular processes, you may not end up having to evict some data just because the other thread that came in didn't end up touching enough data to evict everything in the cache. So in that case, when you switch back to the original thread, some of its data is still in the cache. If it was tagged, it can remain there. And so you have better performance because you don't have misses for all of those.
and is the reason that's not done in general that it adds it adds complexity, and two, it's taking up additional space that you could have used for cache space?
Yeah, it's complexity. It's also, there's a bit of a security concern, which exists even with tagged caches, which is that some malicious program might be able to snoop on another program.
If you're tagged, how would you have the problem? I mean, I guess you could have like a Spectre and Meltdown type of situation, but is there any
shouldn't
outside of
work.
that, or
It shouldn't. You should not be able to read the stuff in the cache without executing a side channel. And so it is a question of a side channel. But then anytime you're sharing any resources, you have some way of leaking information. So yeah, it's a widely open, problem. How do you share a resource without kind of allowing a malicious entity to spy on you, right? Like if you share an office and you left something or you moved something, that tells somebody something. They just can, maybe all they look at is how long you spent in your office, and that tells them something, right? So yeah. Anyway, so coming back to SMT, SMT has a bunch of issues. Cache interference. You have two threads that are competing for cache space. They might be evicting each other's stuff, so that happens. But this is true for any time that you're sharing resources. If you had threads that were kind of like that were SPMD here is single pre-decode multiple dispatch, I think, where you have the same instructions, so you share the iCache, or in some cases you share data and there's less data contention. Typically this kind of stuff is good for server workloads, which is you have workloads that are large, that run for a long time and repeated many times, and they access memory. Maybe right, they're less compute intensive than say scientific computing workloads where it's all number crunching. Here there's more accessing memory and taking data like disk accesses and things like that. SMT, because of all of this cache interference, you may want a larger L2 or a last level cache, which is kind of why you've seen last level caches grow a lot. We've come to an era of like 32 megabyte, 64 megabyte, 128 megabyte last level caches, which is really big. And that's okay, right? Like it typically seems to help performance. So things are happening that way. And then I guess the other thing is map table and physical register files all tend to be really big, and big means they burn more power, slower. So there's a lot of work in how do you make those more efficient? How do you split them up and keep them efficient? I guess another important trade-off there is that when you use multi-threading, you are trading single-thread latency for throughput for the whole system, for the whole process, right? Like any single thread is probably a little slower than it would if it had the whole processor. But then if you are able to decompose your application into multiple independent threads that do independent pieces of work, now all of your whole application will run faster because throughput improves, which is also good for the hardware because there's improved utilization. So the example, so if you had two threads, thread A and B, A has individual latency 10 seconds, latency with thread B is 15 seconds, and thread B was individual latency 20 seconds, improved latency with thread A 25 seconds, right? So if you had if you consider them sequentially, you executed A first and then B, or vice versa. It would be 10 plus 20, so you get total time for execution is 30 seconds. If you executed them simultaneously, your total time is the maximum of the two, so it's 25 seconds. So in this case, adding multi-threading slows each thread down by about 5 seconds, but then improves the total, end-to-end execution time by 5 seconds. Now, of course, this depends on a workload, right? Like if you have a workload that is embarrassingly parallel, it's just there's no shared structure data. You're just doing like multiple threads that keep fetching their own independent data and work well. Your performance improves as you add more threads or cores. Whereas if everything's interchanged, then if everything's interlinked, then your performance goes down as you add more threads. Yeah. So let's look through quite a thought exercise, right? Like if you want to run multiple threads, would you build a chip multiprocessor or a multi-threaded processor? How would you go with this? And kind of why would you do it? These are the answers are on the slide, so fine, I'll go through them. So you could build a chip multiprocessor with multiple separate pipelines, or a multi-thread processor, which is a single larger pipeline, or you could just do both, and that's typically what you see most of the time. You'll see the CMP will mean that you have a simpler, possibly faster clock, so you have smaller things, and then each of those single cores will be multi-threaded, which kind of gives you this ability to translate thread level parallelism into instruction level parallelism. So you kind of get the benefit of both of these types of parallelism. So I think the first few were like this, the UltraSPARC T1, which had 8 processors with 4 threads. So you had 32 cores, 32 threads, whatever. And you had a 1 gigahertz clock in Autoshot pipeline. It was designed for throughput computing, as it's called. And then this is very common today. Most processors in most computers that you can buy will be multi-core and typically multi-threaded as well. Yeah. So you can have all 3 of these techniques in one machine, right? You can have multiple sockets. Each of those sockets has a multi-core machine, and then each core is multi-threaded. So you can have if you have 32 threads, you can have a 2-socket SMP motherboard with 2 chips. Each chip has 8 cores, and then each core is 2-way multi-threaded. So 16 threads in one chip, two chips, you have 32 threads. But the complexity you're essentially taking, you're allowing more fine-grained execution in the hardware, which means that the OS scheduler now needs to make the scheduling decisions, the tougher decisions, right? Like if when it's 2 threads, you can't put maybe you can't put the same you can't put multiple processes on that one processor. Like you have to differentiate between the different types of processors so that maybe they have different accesses to memory. Maybe it's not symmetric accesses to both sides of memory. You have a NUMA machine, then you have to schedule tasks that operate on memory on data in one chunk of memory closer to that memory and the other side, and so on, right? So maybe threads, a task that has multiple threads should go on to the same processor and likely onto the same cores, and if so on. But we've been dealing with these things for about 10 years now, so we're getting reasonably good at using this. Yeah. So I think we're coming to about the end of this discussion. So this is kind of what a server that combines all 3 of these techniques would look like. And this is a pretty dated server, but here these 2 are two different CPU sockets. The CPUs have multiple cores, multiple threads, whatever. These are disks, and you have you have RAM everywhere. Actually, maybe even these are CPUs. They have disk base, so they're probably disks. And then you can scale beyond a single rack, so you can have network links at the scale of a whole. So beyond a single server, you can scale to a rack, right? So now you can schedule operations at the rack level, or across server racks. You see this. It used to be that running a tightly coupled computation across all of the server racks was a supercomputing only thing, where a lot of the way you build things in supercomputers is that communication between, say, a machine in this rack and a machine on the other end of, or maybe just on the rack on the other end of this whatever line, would have to be restricted to a very small latency, right? Like 2 milliseconds is typically what you see in supercomputing. And that kind of is what distinguishes a supercomputer from a data center. But these are making their way into more data centers as well, right? And so talking of data centers is kind of what a data center would look like, right? Or even a supercomputer kind of looks like this as well. So you have a lot of stuff that's just for power, right? So you have some generators, some UPSs, and then this humongous amount of space that's dedicated for making for cooling water. And then you have all this All this black stuff is kind of the cooling pipes and all of that that's going out. And then you have all the racks out here that are, cooled by this water and so on. So what does a data center typically look like? Here's one that's, I believe, under construction. This is, it's reasonably sized data center. I saw some pictures of the ones in Virginia. The Microsoft data center in Virginia is like four or five of these buildings, all just right next to each other. And they're literally sitting right next to the power plant because that's how much power they draw. And just as something that I think is pretty cool, Microsoft research has been exploring this idea of if we're cooling data centers and we need to cool these machines, what happens if we put them in a cool environment, right? Like what if we put some machines into this container thing and then drop it, a couple of 100 meters onto the seafloor where it's really, really cold. Then you don't have to spend as much energy on heat exchangers and things like that. I just include that because I thought it was cool.
So a stupid question, but in the previous picture, when you were talking about Microsoft having like 4 of those data centers, did you mean like 4 of them literally next to each other, or one the size of 4 of them?
Oh no, the one in Virginia is 4 of them next to each other. They're just built in different, phases, right?
Okay. I was trying to think what the benefit is of having, 4 different buildings rather than just one giant one.
Yeah, it's mostly that you can build a Porsche. You can build one, operationalize it, recover some of that cost, and then, it's a capital.
It's a financial decision.
It is also an engineering decision because building larger structures adds more overhead.
Yeah.
So anyway, that's kind of the little. I thought it was cool, so I just added it. And yeah, with that, we are done with this lecture. Actually, have not planned another set of slides for the remaining 15, 20 minutes, whatever. So we can, I don't know, talk about questions or stop early. Questions people have.
Could you talk a little bit about the relationship between the operating system and then what we talked about today? Like, because I know the OS does a lot of process synchronization and process scheduling. And so how do the different systems affect the OS? Like, does the OS get built dependent on these systems? Does that make sense?
Yes.
What I'm asking.
Yes, it does make sense. So I think up till with the introduction of multiple processors, especially with symmetric multiprocessing, the OS didn't need to change because the assumption was, or the complexity was all hidden in hardware. Like maintaining uniform access to all of the memory in the system was established in hardware. Coordination and synchronization, all that was done at hardware. So it was slower, right? Like there's a performance cost to that because you're going, you have to build these complex things. They take time to operate. You have to pass signals between them, all of that. With each of these changes, like CMP coming in and having multiple threads on them and all of that, you're exposing, you're still providing the same interface where if the OS knew no better, it would, make its decisions and things would execute properly, like normally. Maybe they would suffer like some performance penalties, but you're never going to have a correctness problem. At least that's what the hardware guarantees. But with each change, you do have to evolve the decision making in the OS as to where to schedule what. And so yes, with each change, things do have to the OS does have to make changes. For example, with CMP, you might want to put threads that have a lot of communication between them. So typically something that's within the same process, for example, you might want to put them on the same core, right? As multiple threads, or on the same cores on the same chip, for example, just so they can share. They have shorter distance to travel and shared caches and things like that. And then with NUMA coming in, where you no longer have the guarantee that all cores, all chips have the same latency of access to all of the memory, right? So one memory may be closer to another one. Then you have to have, the OS has to be aware of this and make scheduling decisions that factor the differences in memory access latencies while doing its scheduling, and so on. Yeah. I hope that did that answer your question?
Yeah, it did. Thank you. Yeah, I was just trying to learn more about like how much they know. So that was really helpful. Thank you.
Yeah. Yeah. We can also use this time to discuss any other questions that people have, like not necessarily related to this slide. If you're interested about reading about this thing, it's called Project Natick, whatever. But yeah, any other questions? Oh, there's something on the chat.
I just posted a link to it because I was
okay.
looking at it. It's pretty interesting.
Okay. Questions about, I don't know, the rest of the class, exams, I don't know. Are people hoping to take the exam? How many people are actually going to take an exam? I don't know how to...
I'm not like banking on the fact to get points from it, but I'm gonna take it. I want to see like how well I'll do.
Okay, so there's
Take it. Yeah, same.
Okay, so there's some interest in the exam. Okay.
I mean, I have nothing else to do with my life now. There's nothing to do in quarantine, so.
Okay. To take exams. I don't go build something. Yeah.
Maybe the exam can just be an architecture trivia night.
That would be funny. Do you guys want to have a Zoom pizza party?
Sure.
Does that mean I will be provided pizza, or will I have to be spending money on pizza?
Pizza is optional. You can buy your own pizza.
I'll bring pizza emojis for everyone.
Thanks, hey guy. After lecture, can I ask you a quick question?
Yes.
Just about what you were saying with the errors that I was getting. I'm pretty sure that it's not that.
Okay.
And also, the non-blocking assignment was in your code.
Oh.
So if that's wrong, that's that one I can't say is on me.
Damn it. Yeah, we'll talk about that afterwards. Okay.
Yeah.
If no one else, if there aren't any other questions, people are free to drop off. And I'm here to deal with any questions people have.
There's a question asking what the format of the final exam is going to be.
Oh, I don't know. It's going to be...
Could it please be something like multiple choice? Just not.
I mean, it's not
My
going to
bad.
be. It's not going to be. I don't think it's going to be. Free form essays. It's probably going to be like, questions that you can answer in like a couple of maybe like a fill in the diagram or a single word answer. I don't know. I have no idea. We'll see.
I just think if we're taking it online, it's sometimes the easiest just to have multiple choice. Like the multiple choice Sakai ones have gone much smoother than my free response ones. just throwing that out there.
Okay.
I guess we also don't have a Sakai page, so that doesn't help.
So I mean, I guess I will have to set that up for the exam because I don't know of any other way to. Has anyone used anything else for online exams?
Gradescope.
Great.
Yeah, for my
Working on a take-home exam for Gradescope right now.
Okay.
yeah, you give us like a PDF, we print it out, we write it, and then we submit it to Gradescope.
Okay.
I lack a printer.
I mean, you can always fill up with PDF in.
Word.
Yeah, or you could just
yeah,
like
just copy it.
write
into
it on a
Word.
piece of paper.
Okay. Yeah, we'll think about it. I'll let you. I'll figure it out and have a reason. So I think we have about 5 lectures left. I was thinking of covering some amount of synchronization, so cache coherence, cache, yeah, and maybe some kind of domain-specific architecture stuff, so like GPUs or other accelerators, just very basically how they work, how they're different from a CPU and things like that. If anyone, if there are topics people want to have covered instead, we can also post it on Piazza, I guess, and we'll see. All right. I guess if there's nothing else, we can. Yeah, I'll stop recording and then people can drop off as they want.